All right, so we are at section 2.11 talking about the beta distribution. And the beta distribution is going to give us a prior to use when we're doing estimation with the Bernoulli and the binomial distributions. And as you saw in the previous section, these were the distributions we were using to model the tosses of a binary variable, the coin tosses, whether it comes up heads or tails. And we found that, as we described at the beginning, that if we just do maximum likelihood estimation from those coin tosses to get the parameter of the coin, we get some funny results, because the maximum likelihood estimate just measures the number of heads as a fraction of the total number of tosses. And if you have a small number of tosses, then you could very easily have maximum likelihood estimates that tell you, oh, it's your coin is perfectly, it's always going to give heads or always tails. And we want to kind of combine, that seems kind of silly, right? So we want to combine that with our prior information about how coins behave to get more reasonable results. And the question is, what priors do we use? And we're going to see here that certain priors behave nicely in that the posterior, when you combine the prior with the likelihood to give you a posterior, will be in the same family as the prior was. So you essentially just get the same distribution but with different parameters, and that can be very useful. And that property is going to be called conjugacy. So we'll see that. Now this is kind of the third time I'm filming this, because there's a little bit of a confusion in this section, because it's not clear exactly what the estimation setting that we are in. It doesn't actually matter to the results, but it was a little bit confusing whether we're talking about essentially whether we're always going to be trying to estimate the bias of the coin, but is our data going to be the actual history of the tosses, or is it going to be the number of heads? As we saw in the previous section, all that matters is the number of heads. So in both cases, you'll get the same answer, and all of this stuff in the section will go through. But it makes some of the the sentences a little bit confusing. So that's why I had to kind of do a double take and be like, what exactly is he talking about? And just to kind of illustrate that, let me just zoom in here. We can just do a little bit of a. So the question is, whether our data is the history of the tosses, so heads, tails, heads, da 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 da. In which case we said, okay, well, the probability of the data, the likelihood of the parameter is going to be the product over all of these tosses of mu, let's just call it h of I for whether it was heads, or 1 minus mu to and 1 minus hi. So that corresponds to tails. And then we saw that all that matters here is just the number of heads when you do the maximum likelihood. Or is your data just going to be, I have, let's say in this case, it's just the number 3, so 3 heads. So in which case, so it's no longer, you just have one data point, which is the number of heads you have, in which case the probability of your data is now given by the binomial distribution, by the binomial distribution of having picked, m out of n heads. And that's going to look very similar. It's going to be n m, so the number of ways of getting m heads, out of n, times mu 2 to the power of m, and times 1 minus mu to the power of n minus m. And so basically, if you actually kind of add all of these, if you work out what this looks like, so let's actually just do it. So you'll see that, let me move some things around. Let's move that down here for now. So this thing is going to equal to mu times times 1 minus mu times sum 1 minus hi. And these sums are going to be equal to 1. They're going to be going from 1 to n, right? So this is going to be mu to the m times 1 minus mu to the n minus m. Hopefully you can see that. So the point is that the probability distribution and the dependence on mu is exactly the same in both cases. It's just that if you use a binomial distribution, you'll have this additional factor out front, the n over m, because you're not keeping track of where exactly you got the heads. But the dependence on mu, which is all we care about here, It's exactly the same in both cases. So anyway, I thought that was a little bit confusing because he talks about binomial or Bernoulli. It doesn't really matter for what we're going to talk about here, but you know the estimation situation is slightly different. So you're keeping track of data in one case, whereas in the other case you're just keeping track of like the number of heads or tails. So hopefully, you know, anyway, I hope that made some sense. And let me know in the comments if not, and I'll be more clear about that. Okay, and while we're here, let me just make these arrows point to the right place. So this arrow, so this is, that's that, and this is going to be this thing down here. So you use slightly different, but very related, obviously, probability distributions, and the form of the dependence on mu is the same in both cases. This normalizing constant disappears because there's no dependence on mu. So when you're trying to maximize things with respect to mu, this thing doesn't matter. So you're basically in the same boat, and all that matters is the number of heads you get. Okay, so hopefully that wasn't too confusing and kind of gave you some sense of where my confusion was coming from. Okay, so we've seen the maximum likelihood setting for the parameter mu in the Bernoulli distribution, and hence in the binomial distribution, it's given by the fraction of observation in the data set having x equals 1. So that's basically m. It'll be m over n. As we've already noted, this can give severely overfitted results that we just said. And in order to develop a Bayesian treatment for this problem, we need to introduce a prior distribution over the parameter. We need to kind of bring in our knowledge somehow. And now here we consider a form of prior distribution as a simple interpretation, as well as useful analytic properties, but we're going to motivate it. We know that the likelihood function takes the form of the product of factors of the form mu of x, 1 minus mu to the 1 minus x. So that's exactly what we had up here, right? Everything is, you know, mu to the something times 1 minus mu to the something else. Okay, so that's that. Now if we choose a prior to be proportional to powers of mu and 1 minus mu, then the posterior distribution will have the same functional form. So the idea is that if we pick our prior to look like this, for example, then when we multiply it by the likelihood, which has the same form, the result will also look something like this, you know, up to the normalizing factors. Okay, so that motivates, and that property is called conjugacy, so the prior and the posterior having the same form. And so we're going to pick a prior that's conjugate to the, I guess, the likelihood. I don't know what the exact terminology is. But it's going to have this particular form. It has two parameters, so one for mu and one for b. And it needs a normalizing factor so that when you integrate it over the range you're interested in, it integrates to 1, so that it's a valid probability distribution. So that's where these gammas come from. They just normalize the distribution. And you can now compute the mean and the variance, and we'll see why, at least why the mean has the shape it does in a second. And it says the parameters a and b are often called hyperparameters because they control the distribution of the parameter mu. And so what that means is, well, you know, we've got this parameter mu that determines, you know, whether our tosses are coming up heads or tails, but now we've got b and a determining mu. So they're kind of one level up. They're hyperparameters. The posterior distribution mu is now obtained by multiplying the beta prior, so this thing, where is it? Up there, by the binomial likelihood, which is, you know, which is all this stuff up here. And normalizing, so we have to make sure, you know, the posterior is a valid probability distribution, so it'll have some normalizing factor. But as far as our maximum likelihood is concerned, we don't really care about that. All we care about is the proportionality, and that's because, sorry, let me erase this. And that's because you can think of, in terms of maximization, that normalizing factor is just kind of scaling the function. It's not going to change where the maximum is. So that's why we've got this. That's why we've got this proportionality here, because all we care about is where the mu's show up. Okay, so now he says, we said this posterior distribution has the form P, you know, MLAB looks like this. Now what's M? So let's just, this was the number of heads. And now instead of keeping track of the total number of tosses, we can equivalently just keep track of the number of tails. Right, because then m plus l equals n. So you can choose which form you want to keep it in. But if for this particular, to see kind of where what a and b mean in the beta distribution, it's actually helpful to just use this formulation, m and l, So if we go back up here, this is m, and n minus m is going to be L, the number of tails. And the reason why we do that is because it's going to clarify what the beta distribution actually does. Okay, and so we see that this posterior is proportional to mu times m plus a minus 1 and 1 minus mu times L plus b. So it's almost like the m, it's like the a is like kind of it's also like a number of tosses, number of heads, and b is also like a number of tails. So that should kind of give you some clues. We'll come back to these graphs in a second. And therefore corresponds to the number of, so that's he's just saying what L is. We see that 2.17 has, which is down here again, has the same functional dependence on mu as the prior distribution, reflecting the conjugacy property. So that's kind of what we were after, of the prior with respect to the likelihood function. Indeed, it is simply another beta distribution, and its normalization coefficient can therefore be obtained by comparison with 2.13. So all he's saying is, look, you've got this mu of m plus a minus 1, L plus b minus 1. Well, that looks a lot like this thing, but with a and b made different variables. So just plug in, m plus a for a and L plus b for b, and you get the normalization factor. And indeed, that's what you have. So we see that the effect of observing a data set of m observations of x equals 1 and L observations of x equals 0 has been to increase the value of a by m and the value of b by L, in going from the prior distribution to the posterior distribution. So this allows us to, and so this gives us kind of a simple interpretation for the hyperparameters as the effective number of observations of x equals 1 and x equals 0 respectively. So it's kind of like, and a and b are an integer. So it's almost like the prior is going to give you say, well, you can kind of think of it as like before you come into this maximum likelihood estimation procedure, how many coin tosses have you seen in, let's say in your life, or let's say in the last year, whatever, and A will be the number of heads, B will be the number of tails. So you've got some experience, and now you're going to now update that experience with the results of this current data set that you're on. So the cool thing is A and B don't have to be integers. So this might be a good point to actually look at this distribution. So this is the beta distribution for A and B. Remember, A is the number of heads, B is the number of tails. So this is going to kind of give you, it's going to give you a distribution on mu, your parameter, that captures what you think, that captures kind of your prior belief on mu, given you having seen that many heads and tails. So for example, in this one up here, you've seen one head and one tails, and so you essentially have a uniform distribution over all of mu. So there's no bias anywhere. Whereas now you've seen actually 2 heads and 3 tails, and now things are going to start to shift a little bit. It's tending towards being maybe this coin actually has, maybe it's slightly less likely to get tails on it and less likely to get heads on it. On the other hand, you've got you've seen 8 heads and 4 tails, so now your prior is okay. This mu is this coin is actually a little bit more biased. And notice the funny stuff that can happen where A is actually can be less than 1. So you can at 0 and at 1 actually this distribution will diverge. It's going off to infinity. So you can get you can get quite a range of behaviors. Okay. Okay. Right, so we've got the effective number of observations, and A, B do not need to be integers. And so then this is interesting. So furthermore, the posterior distribution can act as the prior if we subsequently observe additional data. So that's the cool thing, right? Like now that your posterior is in the same family as your prior, so you can now use it as a new prior for the next data set. So we can imagine taking observations one at a time, and after each observation, updating the current posterior by multiplying by the likelihood function for the new distribution, and then normalizing to obtain a new revised posterior. So you've got this kind of sequential procedure going on. At each stage, the posterior is a beta distribution with some total number of prior and actual observed values for x equals 1 and x equals 0, given by the parameters a and b. So a and b are just tracking the number of tails, heads and tails you've observed. And the incorporation of an additional observation of x equals 1 simply corresponds to incrementing the value of a by 1, and conversely for the other one. So and we're going to, in this particular example, we're just going to do it for one example. So one step of sequential Bayesian inference. So you start with some prior, whatever it is, and now we have the likelihood function where you just have single observation of x equals 1. So in that case, you'll remember that the probability of x equals 1 given mu is just equal to mu, right? And so that's this function here. And this is what we have. So it's just a function that mu. You plug in mu and you get mu. So that's why it's just a line. And so what you do is you just multiply this, so that you multiply this by this, and you get this after normalization. So now you let's say you were kind of biased towards 0.5 before. You thought it was around 0.5. Now the distribution shifted slightly because you've seen a head. So it's like, okay, maybe mu is actually slightly greater than 0.5. And then as you gather more and more data, the distribution will adjust. Okay, so then he says, we see that this sequential approach to learning arises naturally when we adopt the Bayesian point of view, independent of the choice of prior and of the likelihood, and depends only on the assumption of IID data. I'm not quite sure what he means by that bit. IID means independent, identically distributed. I don't know what he means that it only depends on that, but let's just keep going. And sequential methods, let's zoom out. Sequential methods make use of observations one at a time or in small batches and discard them before the next observation are used. And this is obviously going to be useful if because it's going to be more space efficient, or let's say you're in a real time setting, you have to predict things. They don't require the whole data set to be stored or loaded into memory, so it can be quite efficient. And maximum likelihood methods can also be cast into this framework. I guess we'll see more of that as we go on. Okay, so now he says, if our goal is to predict as best as we can the outcome of the next trial, then we must evaluate the predictive distribution of x. So we have to evaluate p of x equals 1, say, given the data. And so using just the rules of probability, we just say, well, this is the probability. You have to kind of average over your uncertainty over mu, right? So there's no mu here, it's just data. So now you say, well, what is the probability of x being 1 given mu times the probability of mu of that mu given the data. And notice that the probability of x only depends, if you have mu available, then the probability of x equals 1 only depends on that mu. So there's no further dependence on the data set. Mu kind of tells you everything. So the data set determines mu, and mu determines the probability of x being equals 1. And we'll remember that from a Bernoulli coin toss, the probability of x equals 1 given mu is just going to be mu itself. So that's where this comes from, and that's that. And we've already got it. So this is kind of the expectation of we know that this thing is a beta distribution. So essentially what we're computing here is the mean of the beta distribution, and we already have the result above as to what that is, which is m plus a over m plus a. So remember this was the number of heads you've seen in your current data set. This is the number of tails, and these were the prior number of heads and tails, and which has a simple interpretation as the total fraction of observations, both real, so that's m and l, and fictitious prior observations, that's a and b, that correspond to x equals 1. Total fraction of, so what he's saying is this is going to be the number of heads out of the total number of observations. So let's just write that out. So total number of heads equals, number real, so plus number, prior. And this is total number of tosses that include the real ones and the fake ones. So the number of heads plus tails that are real or fake, or not fake, but the prior, the fictitious ones. Okay, it says note that in the limit of an infinitely large data set, so m and l going to infinity, whatever their fraction is, but they're going to go to infinity, the result 220 reduces to the maximum likely result of 2.8. So basically saying that this thing goes to m over m plus l, which is m over n in the limit of large data. So essentially we recover the maximum likelihood solution in the limit of infinite data. And this is a very general property that the Bayesian and maximum likelihood results will agree in the limit of an infinitely large data set. And that kind of makes sense, right? Because that's just saying your prior is just some prior information you have. But if you observe like an enormous amount of evidence, well, the influence of the prior is just going to be very, very small, right? You've just seen so much stuff now that okay, you maybe have a slight bias from the prior, but you're going to be mostly determined by the likelihood. And then he says for a finite data set, the posterior mean always lies between the prior mean and the ML estimate. So again, that's an exercise. Looks like a fun one to work out. Okay. Now for the last little bit. So he says, okay, look, from figure 2.2, we see that as the number of observations increases, so the posterior distribution becomes more sharply peaked. So let's see what that means. He's essentially saying, let's say if, you can't quite, okay, so he's essentially saying that in this setting, we have 5 observations, so 2 heads and 3 tails, and we have kind of a pretty wide distribution here. Here we have a super wide distribution, just 2 observations. Now we have 12 observations, and it's getting quite, the distribution is getting narrow. So is this kind of a general property? So I thought this was pretty cool. I hadn't seen this before, so this is kind of new to me as well. So I'm just going to state what he says, and if I come up with some intuition for these results, I will kind of post a separate video for that. But let's just see what he says. So the posterior distribution becomes more sharply peaked. This can also be seen. Oh yeah, this can also be seen from 2.16 for the variance of the beta distribution, in which we see that the variance goes to 0 for A goes to infinity or B goes to infinity. So let's have a look at that. The variance of the beta distribution is where? Okay, here it is, right? And so if, as A, as A goes to infinity and B goes to infinity, loosely speaking, we're going to have infinity squared on top, and at the bottom we're going to have infinity cubed, right? Because there's a quadratic term and another linear term. So this is going to go to 0. So the point is that, as you observe more and more heads and tails, you're going to get tighter and tighter distributions on this beta prior. In fact, we might wonder whether it's a general property of Bayesian learning that as we observe more and more data, the uncertainty represented by the posterior distribution will steadily decrease. So is it always the case that those posterior distributions get narrower the more data we observe? And so the way he's going to address this, which I think is pretty cool, but yeah, I'll have to go through it to get some intuition for it myself, is that we can take a frequentist view of Bayesian learning and show that on average, such a property does indeed hold. Okay, so he says, now consider a general Bayesian inference problem for a parameter theta for which we have observed a data set D, described by the joint distribution P of theta and D. So it's the joint distribution of theta and the data that we've got. So the following result says that, so what does this thing say? So it says that the expectation over theta, so I guess that's the prior expectation on that parameter, is the same as the expectation over data sets of the posterior expectation. So it's 2 things are happening. So here you are computing theta after seeing the data set, and now you compute the expected value of theta after that. So you're going to get some posterior distribution on theta for that data set. You compute its mean, and that's what this is. And now that mean is going to wiggle around based on the data set that you observe. So if you take the expectation over data sets, you'll actually get the same value as the prior mean. So, and you can actually just show that immediately by using the definitions, but I don't have a good intuition for it. So if I come up with one, I will let you know in a future video. So that's just the way you work it out. But he says similarly, so when it comes to the question of the variance, he says similarly we can show that the variance, so the kind of the prior variance, is equal to this expectation over data sets of the posterior variance plus this additional variance of the posterior mean. And as far as we're concerned, the only thing that matters here is that, so this is a positive quantity, it's a variance, and we're going to subtract it from the prior variance. So the expectation over distributions of the posterior variance is less than that of the prior. So it just essentially just means that on average, your variance will go down, but that's only on average. Sometimes the variance might go up. So for a particular data set, the variance after observing the data might go up, but on average it goes down. So the term on the left-hand side of 2.24 is the prior variance of theta, so that's this thing. On the right-hand side, the first term is the average posterior variance of theta. So here's the posterior distribution, you compute the variance, and now you average that, you pick a different data set, you do the same thing, and then you just compute the average of the variances over all those data sets. And the second term measures the variance in the posterior mean of theta. So this is the posterior mean, and you're just measuring the variance. Because this variance is a positive quantity, this result shows that on average, the posterior variance of theta, so this thing, is smaller than the prior variance. It's just because, right? So you got, expected is equal to variance theta minus the variance on d. So this is a positive. So this is just a number, and this is a positive number being subtracted from it. So this, on average, your variance in the posterior, on average, your variance will be smaller in the posterior, but not always. On average, the posterior variance of theta is smaller than the prior variance. The reduction in variance is greater if the variance in the posterior mean is greater. So if this term is larger, then the reduction is larger, because that's what you're subtracting from that side. But this result only holds on average, and that for a particular observed data set, it is possible for the posterior variance to be larger than the prior variance. So the answer is, on average, yes, things get tighter, but that's only on average. So yeah, so I think this is pretty cool. If I come up with some intuition for these results, I will share that with you. And there's an exercise, I guess, that deals with that, exercise 2.8. So maybe after solving that, I'll have some more insight. But that's basically this section. So we talked about the beta distribution, how it's kind of a useful, prior, kind of a conjugate prior for Bernoulli and binomial distributions, because then the posterior is also in the same family, and then these parameters have like really nice interpretations as the prior number of tosses of tails and heads, and the posterior number of tosses. So you get this kind of really nice updating effect that happens as you observe new data. So it kind of really leads into ideas of kind of sequential estimation, etc. So that's the end. And so next time we will continue, and we will go on to multinomial variables. So we've just discussed binary variables. What happens when the variable can have multiple, can be kind of k discrete values. Great. So hopefully that was helpful. As usual, please let me know if you liked the video, if you didn't like the video, if there's something I could clarify, if I just said something that was wrong, and I can then update everyone, and we can all learn together. And yeah, hopefully see you in the next video.